Okay, we're going to talk about energy here in chapter 3, and then we're going to include some chapter 17 stuff, because in chapter 3 they talk about how to calculate how much energy is transferred when you're not changing phase. So in chapter 17 they talk about how much energy you can calculate when changing phase. So we're just going to put them together. So first of all, definition. Energy is transferred between a system and its surroundings. So we're going to define two things. A system is anything that you are analyzing. So for chemistry, it's usually whatever reaction vessel, whether it's a beaker or some sort of closed calorimeter or what they call a bomb calorimeter, some sort of system that we're going to encase our chemical reaction in. And our chemical reaction is what we're going to analyze. So the surroundings would be everything outside of that. Or you could define it this way. You could say, all right, our system is the actual reaction and our surroundings is the vessel, and then we're going to ignore everything else outside the universe. So again, we're setting up two things. We're defining what is our system and what is our surroundings. Now, here's how this is different than physics. In physics, you always take the point of view of the surroundings. So when I teach the first law of thermodynamics, the equation is a little different than the equation used in physics, because in chemistry we always take the perspective of the system. We're going to take a look at the chemical reaction and look at it from that point of view. So the equations, again, are slightly different from each other. All right, so there are two ways to transfer energy. One is through heat and the other one is through work, and they combine together to make what's called the first law of thermodynamics. So heat, energy transfer, that's the result of contact between two substances of differing temperatures. Okay, so this is a particle physics thing. Two objects come together, the particles are vibrating back and forth, they collide with each other, and heat is what we call translational energy. So in other words, one particle hits another and translates its energy to it. It's a application of the law of conservation of momentum. A fast-moving particle hits a slow-moving particle. The fast-moving particle slows down. The slow-moving particle speeds up. So in other words, a hot particle hits a cold particle, right? We know that the hotter particles are moving faster, and they translate their heat energy to the colder particles. All right, we'll talk about work in a moment. Let's get some notes on heat. They want you to understand heat from a kinetic theory, which means a particle motion point of view. So go ahead and take these notes down. I, of course, drew the hot object with red particles and the cold object with blue particles. I don't know why we do that. Plumbers do that. Like the hot pipes, the handles for them are in red, and the handles for the cold pipes are in blue. Okay, so what they're showing, in order to transfer heat from one object to another, we have to have an interface. The two things have to come in contact with each other. All right, once you put them in contact, here's what happens at the interface. All right, so we have a hot object, we have a cold object. We know that the hot object particles are moving on average faster than the cold object particles. And these collisions where they hit at the interface transfer energy between particles. And it's a application of the law of conservation of momentum. The fast particles slow down during the collision and the slow particles speed up. And then 4, eventually both objects reach thermodynamic equilibria, or what they call thermal equilibria. Now, you don't have to know this, but this condition of putting two objects together and having them reach thermal equilibria is what they call the zeroeth law of thermodynamics. Yeah, real. Zeroeth. Zeroeth. Zero. I don't know why. Now, the other way of translating energy is through work. Now, remember, work from physics is equal to force times distance is equal to work energy. We put a little vector arrow over the force of the work because it's directional. So there are two ways that we could do work. Now, work means overcoming Coulomb's law, right? Force of attraction is equal to K Q1 Q2 over D squared. So what we're trying to do is we're trying to overcome this force of attraction. So the system can do work on the surroundings, or the surroundings can do work on the system. In other words, you get two types of work. You get expansion and you get contraction. So I'm going to put this all together in what's called the first law of thermodynamics. Now again, there's a lot of versions of the first law of thermodynamics. This is the second derivative version. So we're going to say energy of a system. In fact, let's get rid of the system part. We're just going to say energy between a system and the surroundings is going to be equal to Q plus W. And again, this is called the first law of thermodynamics. Okay. Well, there are two forms of Q. Q is heat. And so with heat, we can either have an endothermic transfer or we can have an exothermic transfer. So in terms of the direction of the flow of the heat, remember, we're always taking the perspective of the system and comparing it to the surroundings. So endothermic, that means the system is going to absorb heat, which means that the energy goes into the system, and that's the positive direction. With exothermic, the system goes in, or the heat goes into the surroundings from the system, and that's the negative direction. So heat is moving away from the system in exothermic, heat is moving into the system in endothermic. Now, you already know that. Work is a little more complicated. There's two forms of work. There's expansion, because remember, work, we're trying to overcome the force of attraction. And then there's contraction. So when you have expansion from the perspective of the system pushes on the surroundings. So in other words, the energy goes from the system and then it goes into the surroundings. So expansion is actually the negative direction for work because we're taking the perspective of the system. Now, we don't normally do that in real life. I mean, when things expand and contract, we think, all right, you got to add heat to make it expand. Well, that's because you're taking the perspective of the surroundings. All right, so for contraction, it's just the opposite. Here, the surroundings are pushing on the system. So the energy flow is that the energy goes from the surroundings and then acts on the system. So that's actually the positive direction. All right, so what type of questions will you get on a test? I'm glad you asked. All right, suppose for a moment we have a system and we want to calculate the change in energy, and we know that the system releases, that's not how you spell that, 34 joules while it does 5 joules of expansion. All right, so what is the delta E for this? All right, so let's set up our little equation. Delta E is equal to Q plus W. So now we can substitute in. If we're releasing energy, that's the negative direction. Negative 34 joules. Now we're going to add that to the work. It does 5 joules of expansion. So expansion is the negative direction. So this is going to be plus negative 5 joules. So our answer is negative 39 joules of energy. All right, so we went over what work is. We're going to come back to these conversion factors in the next video. All right, so let's take a look at chemical reactions. We said that a reaction is exothermic if it releases heat into the surroundings, and it's endothermic if it absorbs heat. Now, in order for that to happen, nature tends towards stability in an exothermic reaction. The products are lower in energy and more stable than the reactants. Now, they're going to tell you in this chapter that that's normally a spontaneous reaction. Be careful with spontaneity. Spontaneity depends upon where you are in the universe. For instance, if you want to melt ice, you know that's endothermic. You have to add heat to melt the ice. However, whether that's spontaneous or not depends upon where you're at, because on a day in winter when it's below freezing, you throw an ice cube outside, it's not going to melt. Now, can you make it melt? Yes, you can add heat to it. You can put it on a hot plate and get it to melt. But you're adding the heat, so that's non-spontaneous. The ice will not melt until you add the heat. However, today it's 92 degrees Fahrenheit outside. We throw an ice cube outside, it's going to melt. And it melts without you having to add any energy. That means it's spontaneous. Now be careful again with spontaneity. Spontaneous doesn't mean instantaneous. The ice will melt, but it will take time to melt. The time issue is not a measurement of whether something's spontaneous or non-spontaneous. Spontaneous means it happens without you adding energy. In an endothermic process, we have the exact opposite. We start out with low energy reactants. We're going to have to add energy to it to create high energy products. So these things tend to be usually non-spontaneous, except at high temperatures, because then it can get the energy from the thermal environment. Now, in a reaction, we have what's called a transition state. Remember, we talked about the 4 steps to a reaction. Bring the reactants together, bonds break, atoms rearrange, and then new products form, bonds form. However, most reactions, there's a point where bond breaking and bond forming occurs at the same time. This is called the transition state, or what they call the activated complex. I'm going to talk about that in a moment. And in order to get your reaction to run, you have to provide, or the environment has to provide, activation energy to make that happen. Now, the net energy that's transferred in a reaction has nothing to do with that activation energy. It only has to do with comparing the reactants to the products. All right, so what does that look like? I'm glad you asked. Let's take some notes on it. Can I have you copy this down? So you should go ahead and pause. Okay. This is something called the reaction coordinate, or in this case, a reaction gradient. And it's energy versus time. And a typical exothermic reaction will have an energy curve that looks like this. We have an energy level for our reactants, and then we have an energy level for our products. Now, the green represents the difference in that energy. The difference in that energy is what we call enthalpy, or delta H. It's the heat of the products minus the heat of the reactants, and it's measured in kilojoules per mole. But you get a negative value because delta anything means final minus initial, and your products are final, your reactants are the initial. So products minus reactants, we're going to get a negative value if it's exothermic. And that makes sense because the heat is being released. It's going in the negative direction. Now, the difference between the reactants and the top of that red curve. Now, the red curve is the reaction pathway. And the top of that red curve represents the difference between that and the reactants is the activation energy. How much energy it takes to create the transition state. And the maximum of the curve is something we call the activation complex. So what do you have to do on a test? I would give you a graph, and then I'd say, all right, I'd label each of these parts A, B, C, D, which part represents delta H, and you would point out the 2 parts where you're doing the products minus the reactants. Or I'd say, all right, what represents the activation energy? And you would say, all right, I'm going to identify the top of that curve minus the energy of the reactants. That sort of thing. I'd ask you if a reaction is endothermic or exothermic. So let's take a look at endothermic. And again, you want to pause. Go ahead and copy this down. Now the difference here is that we have a positive delta H because the products are higher in energy than the reactants. Again, you do heat of the products minus heat of the reactants, and that winds up being a positive value. And kJ stands for kilojoules. Joule is about the amount of energy you get for burning a candle for 1 second. Okay. Now this dynamic equilibria thing, that can happen again with particles, with heat, and again, I mentioned this at the beginning of the video, we call that the zeroeth law of thermodynamics. So you got 2 laws of thermodynamics that you did here. You did the first law, which is Q plus W, and you did the zeroeth law. So we're going to come back on the next video, and we're going to come back to these conversion factors for energy and how to calculate the different values from calories and joules. All right? Thank you very much.